and we're going to talk about some different methods. And I'm not going to go into detail on these methods, okay? I just want you to be aware of them so that you can, just have some idea of what's going on underneath the hood when you call a different method. Okay, let me make sure I'm writing in the correct place here. There we go. All right. So we're gonna talk about some methods. Okay, so the simplest one, as you've probably guessed, is what's called steepest descent. And in steepest descent, what we're gonna do is let's say that this is our design space. It looks something like that. We have some initial guess, and we're going to walk. We're going to take a step in that direction. Now the question is how big of a step, and that's something that, if you were using a steepest descent algorithm, hopefully they give you access to that kind of a setting to decide what kind of a step size to use. Now there's different ways to compute that step size, and one of them is by running a line search algorithm. So basically what it does is it computes the gradient at the point, and then it starts to compute a bunch of points in that direction, okay? So it just walks in that direction and computes a bunch of solutions. And if you look at what that is gonna look like, it's gonna look something like that, right? And so then it can say, based off, there's different ways to estimate the minimum along here, and certainly what we want to do is walk along the minimum here so that our next guess, which would probably be somewhere in there, then then we're going to rerun the gradient, but we're just going to walk in this direction a certain distance. How far before we recompute a gradient? Well, that's what this line search is all about. So let me just write a line search up here. So I'm just gonna walk in this direction until the solution starts to increase. And then one way to do this is then to take the 3 closest points and fit a parabola to that and grab the minimum off of the parabola and then say, okay, that's my new, so this would be iteration 1, iteration 2 then would be at where my estimate is for the minimum of that parabola in that direction, where I've held the gradient constant as I've just walked in a certain direction, computed some points there, and found the minimum in that direction, right? And then now we're at iteration 2, we recompute the gradient. This gradient now is going to point us in this direction. So again, I'm going to walk in that direction until I start going uphill, fit a parabola, and that's the distance that I want to take a step in that direction. So, so this is just kind of a basic steepest descent approach, and you can see one of the challenges with steepest descent is that if you have an eccentric design space, it can kind of zigzag its way in here, trying to always walk in the direction of steepest descent. All right. So steepest descent methods there's some benefits, there's some positives and negatives. So let's just talk about some of the characteristics of steepest descent. So number one, steepest descent is guaranteed to go downhill. And this is a really nice characteristic. You're always guaranteed that your next step is going to be lower than your current step, okay? This can make rapid progress when you are far from an optimum, okay? So I'll say rapid progress far from the optimum. But as you get close to the optimum, there are more rapid ways to get to the optimum, okay? And we'll talk about those. But one of the drawbacks, as you can see here, is that it is slow if function is eccentric. Okay, so this is the steepest descent method. Let's talk about another common method, which is Newton's method. Oh, I guess one last thing here under steepest descent is it only requires gradients. It never requires the Hessian to be computed. Okay. Okay, Newton's method is basically it requires both a gradient and a Hessian to be computed at your design point, okay, or excuse me, at your current location. But if your design space is perfectly quadratic, which we saw, here's a perfectly quadratic design space, then Newton's method will find the optimum in a single step. And that's because the Hessian is constant. So once you've computed it at one location, it can tell exactly where the gradient in your design space is going to go to 0. If it knows just the gradient and the Hessian at one location, it can find the optimum in a single step. So that's a really nice positive thing here. So converge in a single step if design space is quadratic. Okay, so one of the drawbacks, I guess, is that it does require the Hessian, which is second derivatives. So requires second derivatives. And why this is a little bit of a drawback is that anytime you take a derivative, especially numerically, you can introduce error if there's any numerical noise in your model. Okay, so let's just draw this over to the right here for a second. So let's say that we have some numerical model that is deterministic, but there's a little bit of numerical noise in it. Okay, and so maybe if we call it at each of these x locations, we're going to get something that looks like this. And if you connect the dots here, you see that there's a little bit of jitter in the solution. Does that make sense? And actually, like I pointed out earlier, all numerical models have some jitter in them if we're looking out. It depends on how many digits of precision we're looking out to, right? And how close we want to get to the actual optimum. Well, you can imagine now taking a finite difference step here between two locations. The size of that step is going to significantly affect the derivative that you get out of this, depending on how much noise is in the model compared to the signal of the derivative. This is a signal to noise ratio type of thing here, right? So we want a model that has a really strong signal, really clean signal compared to the noise, and so that our derivatives are clean. But then this is amplified, or the error that you can get out of these numerical derivatives is amplified when you're computing higher order derivatives. So what I've drawn here is just a first derivative, right? But then let's say we use these 3 points to compute the second derivative. Well, that's going to fit a parabola that looks like that, which is completely erroneous for this case. Does that make sense? So anyway, so needing second derivatives is challenging because that you can have accuracy issues with those derivatives, and it's more computationally expensive because you need not only first derivatives but second derivatives at a single point. Okay, so that's kind of a con of the methods that require the higher order derivatives. Okay, and then finally, strictly speaking, the Newton's method all by itself is not guaranteed to go downhill. And and that's because what if your design space actually is an inverted parabola? From the first and second derivatives at any point along there, it can tell you exactly where the gradient is going to be 0, but that may be a maximum, it may be a saddle point, it may be a minimum. Okay, and so there's no guarantee that your next step, or where it says that the optimum is actually a minimum, or the global minimum. Okay, it's not guaranteed to go downhill. So it can find saddle points, maximum, or minima. Okay, so what we'd really like, in our wildest dreams in gradient-based methods, is we'd really like a solution that started off as steepest descent and then moved towards Newton's method as it got closer to the optimum. And that's because most, well, maybe I shouldn't say most, but many optima, as you get really close to them, they actually are very nearly quadratic, okay? If you were to zoom in, if we go back to, to these types of things, if you were to cut the design space right really close to that optimum, you can usually fit a quadratic design space to these when you're really close to the optimum. Does that make sense? But far from the optimum, it may be very far from quadratic. And I'm not sure if this is quadratic or not just by looking at it, but far from the optimum, this probably is not. And so what we'd want to do is start off steepest descent and then move towards a Newton's method as we get closer. And so there's a whole family of optimization algorithms. These are called Quasi-Newton or variable. Let me just write this out. Quasi-Newton, or they're sometimes called variable metric methods. And basically what they do is they start out close to, start with steepest descent, and then they move towards Newton's method as they approach the optimum, or as they progress along the optimization. Okay, now one nice thing about how many of these are set up is that they actually do not require second derivatives to be computed, and instead they estimate the second derivative by knowing what the first derivative is at different locations in the design space. Okay, so in other words, so what happens here? Let's just draw another design space, and so let's say we start off right here. We're going to take the first derivative there, and then we're going to progress in our optimization, and we're going to now get another first derivative at another location. Okay, now if we retain the information that we knew at that first point, and we now include it with the information that we know at this next point, we can estimate what the second derivative of this design space looks like, or what the Hessian looks like, based off of this previous information. Okay, and so you kind of get the best of both worlds. You never actually have to compute the Hessian numerically or analytically. You estimate it as you progress throughout the design space. You're able to estimate it from the first derivative information at multiple locations. Okay, so that's a nice benefit. Does not require the Hessian to be directly computed, I'm going to say, because it is estimated, but you never directly compute second derivatives. Okay, there are also methods in here that are guaranteed to go downhill. So I'm going to say guaranteed to go downhill. And these can handle eccentric functions really well. So I'm just going to put eccentric functions. They don't have an issue with them. Okay, so there's a few different ones. We're just gonna name a few of them. So one of the earliest ones was called a rank 1 Hessian inverse update. Okay, so really not used much more. This has been superseded by much better methods, but you might see this out there in the literature. Rank 1 Hessian inverse update. Later, there's one that was developed by Davidson. It's called the Davidson-Fletcher-Powell. Or you might see it DFP. And that was actually used for many years, okay, or for quite some time. Now, let's put things into perspective for just a minute. We're talking about computers as we know them today, right? Where we can code this up and immediately get a solution out of this. But walk back to the period pre-1960. Let's walk to the 1940s for just a minute. And World War II, you're trying to find the optimum solution to something. You know, the way that they would solve matrices, for example, is they'd have 100 people come and sit in a room in a matrix form, right? And each of those people was one cell in the matrix. And they would pass information to each other and with their slide rules compute what their cell value was. Pass information to each other, compute what their cell value was, right? This is how they solved things before they had a computer that could handle all of this. And so these methods were used even before the computer was developed, as I understand. Okay. Now, I guess I don't have proof of that, and we'd have to dig back in history to understand it more. I don't really know the history very well of optimization, but I'm fairly certain that these types of things were being done, and these methods were they're trying to figure out how do you find the optimum in this design space using numerics, but not numerics as we know them. And so these types of computational savings were really important to them as well back then. Okay, in about 1970, so this is 10 years after the computer, basically, if you say 1960s is when it was kind of developed, then there was a group of 4 people. So Broyden, Fletcher, Goldfarb, and Shano. And so they developed a method called the BFGS method. Now, the thing that's so cool about this method is that all 4 of them independently developed this method. And they all published it in that same time frame, in the 1970-ish time frame, but they developed it independent of each other. So 4 people came up with this exact same method, independent of each other. So anyway, it's called the BFGS method. We give them each credit for it. And this was developed about 1970, okay? And this is a very widely used method. And basically, it works just as I explained here, where you're just ever computing gradients at each point that you move along the optimization. But at each point, you're also updating what you think the Hessian looks like for this design space, okay? And so this is a method that converges more rapidly, I believe, for most situations compared to the previous one, or the previous methods out there. Okay, so these are 3 of the main, what are known as quasi-Newton or variable metric methods. So anyway, do you guys have any? I'm not going into detail on this, obviously. Let me just pull up something that might be. This is out of I think this is okay to share. Let me see if I can. Let me just zoom in on what the the BFGS, you have this thing called an update. Okay, so this method, the BFGS method, is very similar to the DFP method, except that it's less sensitive to our line search steps. So for each of these methods, we've got to choose, how big of steps are we going to take? Sorry, up at this line search. How big of steps are we going to take as we move along this line search? And the BFGS method is less sensitive to that. Let me just zoom in on this particular equation so you can see what this equation looks like. And maybe going to Wikipedia would be better. I'm pulling this out of a book here. Actually, notes that were given to me years ago when I took the optimization class. So anyway, here's the this is an update matrix that's being used to update your Hessian. And so you can see how kind of nasty it is, but you use some previous estimate for this matrix, and you're getting a new estimate for it, and it's dependent on a bunch of different things here. But you can see this delta x, like that's your change in x from your previous point. And anyway, basically what it's trying to do is get a better representation for the Hessian as you move towards the optimum. Okay, let's talk about a couple more. And by the way, by far, I am most familiar with the BFGS method. There are a few more that I want to mention because you'll run into them. One of them is called the conjugate gradient method. And I'm fairly certain this is the one that's in Excel, that default in Excel. And basically the conjugate gradient method is a steepest descent method, but it employs a correction factor for the search direction. Now, I don't really know what that means. I mean, I guess technically you could say that that's basically the same as these others. I guess that's not really true because, but they're kind of similar, right? So you're starting off steepest descent, but you're employing a correction factor for the direction that you ought to be walking in. And basically what we're doing up here with these is using the Hessian to do that. I'm really not sure what the correction factor is for the conjugate gradient method, how they're doing that. And maybe somebody else on the call knows. Anybody have something to add to that? Okay, sorry, I just don't have much information on it. I'm not really sure what they're doing. There's a couple more though that maybe you want to be familiar with. One of those is called sequential, let's see, sequential quadratic programming. Okay, you can see that word quadratic in there again. And I haven't dug into this. Actually, Corey has. So maybe, Corey, you want to mention some things here. But this is known as the SQP method. And then there's a variation of this called SLSQP. SLSQP. And this is the same sequential quadratic programming, but the LS here in the middle stands for least squares. And one of the benefits of SQP or SLSQP is that it can handle constraints. All right, and we're going to talk about those here next. But so it can handle constraints where the BFGS method, as it is, or any of these other ones, these are technically unconstrained optimization. We can't. None of these methods are really set up to handle constraints. Right out of the box. So, but the SLSQP method or SQP method, and also the GRG method, which I think that's kind of similar to the conjugate gradient method, but anyway, those ones can handle constraints. So those are some real definite benefits to those methods.
If you want, Dr. Unsaker, I can fill in a couple details there.
Sure.
So I don't remember precisely. I've coded up at SQP and GRG. Sequential quadratic programming is very similar to Newton's method in that it's trying to fit parabolas and it's trying to step to the vertices of the parabola, but it does it has a really fancy way of tying in constraints, like you said. The interesting thing about SQP as far as constraints, though, is that SQP is not guaranteed to satisfy your constraints at every iteration, but only at the end. The GRG algorithm is much more similar to a Quasi-Newton's method, except that so GRG is generalized reduced gradient, and that reduced gradient is when it's calculating search directions, it takes constraints into account, and it will either make sure it's stepping away from constraints, or it will make sure that it's stepping along constraints. So it observes the fences that you put up in your design space. So unlike SQP, GRG always satisfies constraints.
Okay, so always satisfies constraints. Not always satisfied during, and this is during the optimization method. It is going to satisfy them at the end, the SLSQP, but not during, right?
Yeah, that's right. And another thing is with the SQP algorithm, it's, like I said, it's more like a Newton's method, and it's doing a whole bunch of jumps to try and find these minimum points, whereas the GRG executes line searches, and so it'll calculate that reduced gradient. It'll calculate that reduced gradient that is the optimum search direction while satisfying constraints. It'll throw out a whole bunch of points in that direction, and then it'll check each one of those points, and if any of those points are not satisfying constraints, it will push them back into feasible space, and then it will run the and then it will check the objective function to each one of those points to find the minimum one. So before it ever evaluates the objective function, it's enforcing constraints.
Okay.
Which makes it quite robust.
Okay, great. And actually, that means I need to correct something I said earlier. I think somewhere in here we saw a reduced gradient. Reduced gradient here. So I was wrong on what that reduced gradient means. Because we were running the GRG method, this reduced gradient is what you're saying. It's relative to the constraints, right?
Well, it's
not necessarily the scaling, although maybe it's including both. But.
Yeah, I'm not sure about scaling, but yeah, it's your objective function gradient, but it's also taking constraints into account to make sure constraints are satisfied.
Yeah. Okay. Okay, great. Thank you, Corey. Okay, let's see. We've got about 20 minutes left. So I would like to, oh, gee, we may not get through all of this. Let's see. Okay, that's all right. I think today we're just gonna stay in Excel. We're gonna do a couple more things in Excel, all right? I had something we were gonna do in Python. I think I'm gonna save that for tomorrow. And instead, we're gonna stay in Excel for today. Let's talk about bounds and constraints here really quickly.